All right, in this video, we're going to talk about the t-test, so the statistical analysis using a t-test. We'll give you some background information, how to sort of interpret that both statistically and biologically, and then how to conduct one in RStudio. Okay. So a t-test requires a categorical X, which is your categorical independent, so treatment, population, species, right? Um, and generally it's going to be two levels, right? So three or more levels of a categorical action we would be doing. In ANOVA, when we have one or two levels, we would be doing a t-test. More specifically, we're going to be looking at a two-sample t-test, but I'll talk about some differences here in a second. And then our dependent variable, or y, needs to be a continuous numerical variable. So we need one continuous, one categorical. The categorical should be the independent. The continuous should be the dependent. So really the most common use of a t-test is to compare two population means or two sample means or two treatment means, right? So we obtain two samples, one from each population. We set the null hypothesis that there is no difference between population means. So the mean of one equals the mean of two. And specifically here we're saying that the means are the same, or that there's no difference in the means. Then we looked at the expected distribution of the t ratio concerning the difference between the two population means. And we compare the t ratio calculated from our sample data with the expected under the distribution for the null hypothesis. So basically our observed t ratio versus the distribution of the t ratios. And we can decide to accept or reject our null hypothesis based on that result. Okay. So again, we're going to focus on a two-sample t-test, but like I said, there's actually other ways to do this. So there is a one-sample t-test where if we have one sample, we can test if your sample mean is different from some set value. So is your sample mean different from 0? Is your sample mean different from 10, right? We would need a reason for that value, so 0 or 10 in my example, to be biologically meaningful, and wanting to know why or if our treatment mean was different from that value, but we could do it with a single sample. Okay. Again, the null hypothesis is the sample of the mean is equal to whatever value we choose. Okay, or the sample mean is equal to whatever value we choose. Paired t-test. This is usually one sample, but we take it at two different time points most commonly. So it's data in pairs, before and after, right? Pre and post. So we basically would measure the individuals, do some sort of intervention, and then measure them again and look at the difference between our pre and our post, or before and after intervention values, to see if those means differ. But again, the most common is the two-sample t-test here. So we have two different populations or two different treatments. We take a sample from each, and the null hypothesis is that the mean from one is equal to the mean from the other. Okay. So again, we're going to focus on the two-sample t-test for the rest of the tutorial. The null hypothesis is that the mean for one equals the mean from the other, or another way of saying it is that the mean of one minus the mean of two is equal to 0. Okay. The alternative, again, would be that they're not equal, so the mean of 1 does not equal the mean of 2, or the mean of 1 minus the mean of 2 does not equal 0, right? The difference in the null hypothesis doesn't have to be 0. It can be some biologically relevant difference. Again, similar to a one-sample t-test, if we have a value that has some scientific relevance, we can test for that difference. Okay. The t ratio, or the t statistic, is determined by the difference in the means divided by the pooled standard error of the two means. Okay. And so again, the denominator is the pooled standard error. The numerator is just the mean of one population minus the mean of the next population. We can do a one-tailed versus a two-tailed t-test. And so these distributions represent the t distribution, right? If we do a one-tailed test, so if for some biological or scientific reason we expect the difference to be greater, like in a specific direction, so we expect the mean of population 1 to be greater than the mean of population 2, we can look on just one side of that distribution to see if that's fitting, right? Or if it's less than, we can look on the other side of the distribution, right? So basically with an alpha of 0.05, we're looking to see if our t ratio falls with less than 5% of the area on the other side, right? So a one-tailed t-test, we really are implying direction. We're looking at one end of the distribution to see if the value is greater or less than, right? That's not nearly as common, but you can do that again if you expect a direction in your difference for some biological reason. More commonly, we do the two-tailed t-test, so we look on both sides of the distribution, just asking if they're the same or not, right? So if we're not concerned with the direction of difference, just if the two samples are different, we would do a t-tailed. If for some biological or scientific reason we wanted to test for a specific difference in a direction, so either greater than or less than, then we would use a one-tailed t-test. Okay? So let's look at an example. We can look at how different drugs affect current sleep amounts. So we have drug A and drug B. We measured how much the sleep amounts changed in patients compared to before they started medication. So all of these patients had the amount of sleep measured. They were each given a different medication, and then their sleep measured afterwards, and this is sort of the difference in their average nighttime sleep. So if it's negative, they got less sleep. If it's positive, they got more sleep. And then we have the two drugs, drug A and drug B. And so this is a two-sample t-test, right? So what's the null hypothesis and what's the alternative hypothesis? Okay. Well, then the null hypothesis here is that the mean change in sleep amount for drug A is the same as the mean change in sleep amount for drug B, or the drug A mean equals the drug B mean. Okay. The alternative is that those don't equal, right? Mean change in sleep amount for drug A is not the same as mean change in sleep amount for drug B. Again, if we wanted to do a one-tailed t-test, we could say is greater than or less than, but we're just asking if they're the same or different. So this will be a two-tailed t-test. Hey, how we do this, we calculate the means for both group, we calculate the variance for both group, then we calculate the pooled standard error, and then we use that to calculate the t ratio. Okay? Again, you don't have to do this by hand, but it is quite simple, right? So the means, here drug A is 0.75, drug B is 2.33. The variance, drug A is 3.2, drug B is 4.0. Pool standard error, 0.85. Y1 minus Y2, so 0.75 minus 2.33 divided by 0.85, right? That's our equation for the t ratio. I guess it's a t ratio of negative 1.86. I apologize. The degrees of freedom, because we're actually calculating two means, is the sample size of 1 plus the sample size of 2, or the total sample size minus 2. Okay, so n1 plus n2 minus 2, or just capital N minus 2. In this case, we had 10 participants in each group for 20 samples, so a degree of freedom of 18. Our t ratio then was negative 1.86. Degrees of freedom was 18, and our if we look that up in the t distribution, that gives us a p-value of 0.11. So how do we interpret those results? Again, since our p-value is greater than our 0.05, the alpha that we give you as a cutoff, again, which is totally arbitrary, we fail to reject the null hypothesis and say that there is no difference in the mean change in sleep for drug A versus drug B. As in all statistical analyses, there are assumptions here. Okay. These are never exactly met, typically, but some of them are more important than others, and some of them we can be robust about, some of them we cannot. So one is that it's a random sampling, right? All the samples need to be random and independent of each other. That cannot be fixed regardless of what you do afterwards. That's in your experimental design. Okay, so again, random and independent. Homoscedasticity or homogeneity of variance basically means that your error or your variance is similar and normally distributed. And again, normality here. Okay. Let's look at an example. Here we have a categorical independent variable, whether there was a treatment or a control, right? And then we have the height of the plant and the mass of the plant. Okay? So to visualize those data, we make box plots just like we would in ANOVA, with the continuous variable being the dependent variable is on the y, and the categorical independent variable on the x. So here's plant height by treatment. Again, the bars represent the total range of the data. The black line indicates the mean, and the box is your first to third quantile, and outliers would be circles outside of this. Okay? Here's plant mass by treatment. Okay? So there's our visualization, a box plot just like in an ANOVA, because again, a t-test and ANOVA are very similar. It's just ANOVA is used when we have 3 or more levels of our categorical variable. A t-test is used when we have 1 or 2 levels. Okay? We can do a t-test simply by the t.test function in base RStudio. Very simple. Gives you a t value, so negative 1.3691 in this case, and here we're looking at the height and if that differs between treatments, the degrees of freedom, and the p-value of 0.1913, and it actually spits out your treatment means as well, and your 95% confidence interval. Okay? And so because our p-value is greater than 0.05, again here we would fail to reject the null hypothesis and say that the mean plant height for treated plants versus control plants is not different. This one is doing the mass by treatment. Again, just t.test. We give it the y, the x, and the data. Here our t is negative 0.2, degrees of freedom 17.889, p-value of 0.84, and there are our means, again failing to reject the null hypothesis and saying that there is no difference in plant mass between the treatment and control groups. Okay? What does this look like in RStudio? Again, it's very simple. So again, the first thing I'm going to have done is have downloaded the data set, moved it from my downloads folder into my folder that I use for my working directory, ensuring that it's a CSV file, just like every time, right? This is something you need to learn and understand, and that happens first. Download the folder or the file as a CSV, move it to your working directory, making sure it's still a CSV, open up RStudio, set your working directory, okay? And then import your data. This I'm just going to call plant.data. So again, all I'm doing is telling RStudio to create an object, and to that object I'm going to assign, that's with the less than dash sign, and I'm going to assign it this CSV file by saying read.csv. Okay, and now I see that in my environment window I've got plant.data. If I want to view this data, so in this data set I have 2 plant types, a highlight plant and a low light plant. I have photosynthetic rate and transpiration rate and par level. I'm going to leave par level off, but we can think of the plant type as our independent, and then have 2 dependent variables, photosynthesis rate and transpiration rate. Okay, if we look at the structure of our data, str plant data, again down here, spits out the variables, the type, 55 observations of 4 variables. Okay. Now we visualize our data, again to make a box plot. So box plot and then y variable. In this case we're going to do photosynthesis rate first, tilde, and then our x variable, plant type. Okay. So photosynthesis rate tilde plant type, comma. Then we have to tell it what data file to look in. Data equals plant.data, comma, label our x-axis, xlab equals plant type, low or high light, in quotations, comma. Label our y-axis, ylab equals photosynthesis rate, again in quotations, comma. The main label for our visualization equals photosynthesis rate by plant type, all in quotations. And then I want to assign colors to my boxes. Again, this is treatment versus, or no, highlight versus low light. Again, RStudio does this in alphabetical order, so the first color I list will go to highlight, the second color I list will go to low light. But COL equals, so color equals C, which is concatenate red to highlight, blue to low light. If I run this, okay. Now, these boxes don't look like boxes, right? But it spit out a box plot, so you should know that the code is right. The problem here is that there's not a lot of variance in the data, and so, but this one outlier here, so this guy way out here, negative 500, is pulling that y-axis way down, and so it squishes your box plot. Okay. One thing we could do is go back to our original data and check that data point to make sure it's real. Or that it's not an error, and then we can go back and fix that. Okay. For now, I'm just going to leave it. But again, you can see that it's got those open circles, which are outliers, and we can see these really squished boxes. That doesn't mean that you did the code wrong. It just means that this outlier here is pulling it way down, right? So all these values are around 0, and this value is down around negative 520, right? So it's really skewing the scale of that y-axis. We can do the same thing for transpiration rate. So all I do here is change transpiration rate instead of photosynthesis rate. That's my Y, there's my X, there's my data. Now I adjust the axes labels and I assign purple and green as the colors. Okay, again, now we've got purple and green. Again, these outliers are sort of squishing down that axis there, or actually they're pulling that way up. Because this one is way higher than the average. So the boxes look squished. It's not an error in your code, it's the data, right? So RStudio creates the plot that you told it. As long as it creates a plot, your code is working. Now you might have flipped your axes, or your data might not be 100% correct, and therefore the plots might not look like they should or could, but that doesn't mean your code isn't working. So in both these cases, the data is messy, so the box plots don't, I'm going to use air quotes, but you can't see me, right? The box plots don't look good, but the box plots are accurate given the data that we've given RStudio, okay? Then we can conduct the actual t-test. We just do that with a t.test, and then the same start as the box plot here. Here's photosynthesis rate is the y, tilde here, oops, and then x, plant type. So if we run this one, now it spits it out here. Data photosynthesis rate by plant type. Our T ratio is 1.0395. Degrees of freedom 27. P-value 0.3078. And there's our means. Okay. Again, since our p-value is greater than 0.05, we fail to reject the null hypothesis. This suggests that the mean photosynthetic rate for highlight plants is the same as the mean photosynthetic rate for low light plants. Okay. We can do the next t-test on transpiration rate. Again, all I do is actually change photosynthesis rate to transpiration rate, otherwise the code's the same. Now it spits it out down here. Again, T ratio is negative 1.1153, degrees of freedom 27, p-value 0.2743. Again, here's my highlight mean and my low light mean. Again, my p-value is greater than 0.05. I fail to reject the null hypothesis. The null hypothesis, which means that transpiration rate of highlight plants, I should say the mean transpiration rate of highlight plants, does not significantly differ from the mean transpiration rate of low light plants, right? Or the difference between those means does not significantly differ from 0. Okay, and that's how we run a t-test.